Hello friends, welcome to my YouTube channel Engineering Modules. So today I am going to discuss you about transient analysis of series RLC circuit with DC excitation. So before starting this topic, I note that in the previous two videos I describe about time domain analysis of series RC and RL circuit with DC excitation. They are first order circuits, but in this video I am going to discuss about series RLC circuit. This is second order circuit. So let's draw the circuit diagram. So the circuit diagram is, so this is the circuit diagram of series RLC circuit. So now at t equal to 0 plus, which means that after the switch is closed, at the time the voltage source supply the currents, and then if we apply KVL through the circuit, then the equation that will be formed is like this IR plus L di by dt plus 1 by C integral I dt equal to V naught. V naught is the supply voltage, and IR is the voltage drop across R, L di dt is the voltage drop across L, and 1 by C integral I dt equal is voltage drop across C. So now computing this equation, we get L d2 dt square plus R di dt plus I by C equals to 0, and modification with this we get that P square plus R by LP plus 1 by LC into I equals to 0, where P equals to d2 by dt square. So now we see that from this equation we says that P square plus R by L P plus 1 by LC equal to 0. So this is a quadratic equation. So it has two roots. So now calculate the characteristics equation and find the roots that are called P1 and P2. So now calculate. So by the solution of the quadratic equation we get that P1 comma P2 equals to minus R by L plus minus root over R by L whole square minus 4 by RLC by 2, and this we get that alpha equals to minus R by 12 and beta equals to root over R by 12 whole square minus 1 by LC, and P1 equals to alpha plus beta, P2 equals to alpha minus beta. This is the solution of differential equation of this differential equation, where P equals to d2 by dt square. So now we come to the solution of the differential equation, and it becomes, so the solution of the differential equation is I equals to C1 e to the power P1d plus C2 e to the power P2t, C1 and C2 as constant. We get this differential equation from the second order circuit differential equation. We know all that this is the constant terms of the differential equations, and this is the solution of a second order differential equation. So now we have three cases because we have beta, that is root over R by 12 whole square minus 1 by LC. So the cases are, so in case 1, when r by 12 whole square greater than 1 by LC. So what we say, when the discriminant is greater than 0, then beta is real and positive. So by putting P1 and P2 value in their position, we get that I equals to e to the power alpha t into C1 e to the power beta t plus C2 e to the power minus beta t. So by seeing this equation, we know that the current response is overdamped because the curve is indicating a overdamped curve. So how the curve looks like? The curve looks like as this. This is a peak and this is decreasing gradually. This is overdamped condition, and this is I, this is T. So this is the condition and the graph when R by 12 whole square greater than 1 by LC or discriminant greater than 0. So the next case is when R by 12 square less than 1 by LC or discriminant is less than 0, or when the discriminant is imaginary or complex, then the P1 and P2 are complex quantities, alpha plus JB, alpha minus JB. Okay, so the current makes the equation that I equals to e to the power alpha t C1 cos beta t plus C2 sin beta t. So this is the equation for a oscillating curve. So the solution of the current is underdamped or oscillating. So what is underdamped? The amplitude of the curve or peak value of the curve is gradually decreasing. So the curve looks like this. I and this is T. So the curve looks like as this. So now the third case. So case 3, when R by 12 whole square equals to 1 by LC and the discriminant becomes 0. So now the current becomes e to the power alpha t into C1 plus C2. Then the current graph becomes a critical damped response. That is a peak value at this decreasing main handle. This is critical damped. It's a peak value. Then I and this is T. So this is critically damped and this is underdamped or oscillatory and the first one is overdamped. So this is all for transient analysis of RLC circuit with DC excitation. We have discussed about the differential equation that we formed in the equations and all about the cases when discriminant are greater than 0, less than 0 and equal to 0. So this is all for today, friends, and keep watching and please like, share and subscribe my channel, and thank you. And in the next videos I am going to provide you some more things about electrical engineering. And welcome to my YouTube channel.